This is Shop Talk. 3000 RPM throws beautiful chips in aluminum and turns a steel tool blue in 30 seconds. Same spindle, same machine, same number on the screen. The number isn't the problem. The number you're looking at isn't the one that matters. When you write S3000 in your program, you're commanding spindle revolutions per minute. That's it. The controller doesn't know what tool you loaded, what diameter it is, or what material is in the vise. S3000 M03. Spin the spindle clockwise at 3000 revs a minute. The block says nothing about how fast the cutting edge is actually moving through metal. The number that matters is surface feet per minute, SFM. It's the linear speed of the cutting edge as it sweeps through the work, feet of material passing under the tooth every minute. Two tools, same RPM, different diameters. The bigger tool's edge travels farther on every rotation because the circumference is bigger. Same spindle speed, totally different surface speed. Here's the formula machinists actually use. SFM equals RPM times tool diameter in inches times pi divided by 12. Rearrange it and you get RPM equals SFM times 3.82 divided by diameter. Aluminum likes to be cut fast. Carbide in 6061 runs comfortably at 800 to 1000 SFM. The material is soft, the chip carries heat away with it, and the edge can move through it without piling up energy. Steel doesn't. Carbide in 1018 wants 200 to maybe 400 SFM depending on the grade. Push it past that and the heat has nowhere to go. It dumps straight into your cutting edge. Aluminum tolerates roughly 4 times the surface speed of mild steel. That's the whole story behind the burn tool. Run the math on that 3000 RPM with a half-inch end mill. Pi times 0.5 times 3000 divided by 12. You're at about 393 SFM. Perfect window for steel. Way under aluminum's sweet spot. You're leaving cycle time on the table. Now swap to a 1-inch end mill at the same 3000 RPM. You just doubled the SFM to almost 790. Still fine in aluminum. In steel, you're cooking the edge before the first slot finishes. This is the trap. Most shops program RPM directly when they should be thinking in SFM. So a number that worked for a half-inch tool gets copied onto a 1-inch tool, and the operator wonders why the new program eats inserts. On a lathe, the problem gets worse because the diameter you're cutting changes as the tool moves toward the center. Same RPM, but the surface speed at the edge drops every second the tool feeds in. That's why lathes have G96, constant surface speed. You command SFM directly, and the controller ramps the RPM up as the diameter shrinks. G50 caps the maximum, so the spindle doesn't try to do 9000 RPM when it hits center. On a mill, you don't get that luxury. The diameter is fixed by the tool, so you do the math once, set the RPM, and trust the geometry. Which means the math has to be right. Pick your SFM from the material first, then derive RPM from the tool diameter you actually have in the holder. That order, material first, tool second, RPM last, is the order most programmers do backwards. Here's the worked example for steel. Target 350 SFM, half-inch tool. RPM equals 350 times 3.82 divided by 0.5, about 2670 RPM. Same target SFM with a 1-inch tool drops you to 1335 RPM. Half the spindle speed, same cutting condition at the edge. So, when somebody says 3000 RPM cuts aluminum clean and burns steel, the RPM isn't really the variable. The hidden variable is tool diameter, and the controlling variable is SFM. The spindle number is just the output of those two. If you've made it this far, you already think differently about the S word than most operators on the floor. Subscribe. The next videos cover G96 constant surface speed, chip load, and why feed per tooth is the other number nobody talks about.